Remember this? I've been vomiting and I felt burning pain in my chest and abdomen areas after I drank something. And I honestly suspect that my drink has been poisoned. Okay, so as a chemistry teacher, I need to apply all my skills to find out what is the harmful thing that I've drank. Okay, so today's lesson will be on qualitative analysis. Alright, so we will have this training program first to be equipped with all the skills to identify what are the unknowns in a solution. Okay, so there are three parts to it. One of them, of course, is to construct the knowledge first. Okay, then we need to constantly recap before we can solve the case. Okay, so there are few parts. First of all is to identify the unknown gases. Okay, and then anions and cations. Okay, so we will do tests for gases, tests for anions first. Okay, then we move on to anions and cations where we recap the science behind it. Okay, then the last part, of course, we need to have a quiz to test our knowledge to see whether we can remember all this. Okay, so what is qualitative analysis? Okay, fill in the blanks inside your notes, page 2. Qualitative analysis is to find out what is the unknown. Okay, we want to detect the ions inside, and then we do so by activating our senses. Okay, where we take note of the color change, we take note of the precipitate formation and the gas formation. So precipitate is your solid. So we are not interested in the quantity. We are not interested whether the unknown contains a lot of this or a lot of that. Okay, we are only interested whether it contains or not. So that's the difference between qualitative versus quantitative. Okay, so we are looking at analyzing what is the unknown, not the quantity. Okay, why do we learn about QA other than helping Miss Bay to solve a mystery? Okay, real life application will be, of course, to analyze what are the ions inside the blood. So you have your blood test. Okay, and of course, um, you want to test whether your drinking water is safe and what are the dissolved cations and anions inside. So QA is to analyze unknown salt, unknown gas, and they will have cations and anions. Okay, so let's say we have an unknown salt, and this unknown is copper 2 carbonate, but we are not aware of the identity. Okay, however, we learned that this one, the salts, right? All the salts they are produced, they are ionic compound. Okay, so for ionic compound, definitely it must contain cations and anions. So for this unknown, the cation will be Cu2 plus and CO3 2 minus. Then sometimes this ionic compound, right, when they react with acid, sometimes they will produce gas. And then we observe effervescence. Okay, so there are three unknowns. So we need to test for gas, we need to test for anions and the cations. And sometimes the unknown, right, they are colored. So once you see colored solution, colored solid, so it can be in solid state, it can also be in solution state or aqueous state. So please write down. Once you see color, straight away it means transition metal. Okay, and transition metal are between group 2 and 3. The one in the center of your periodic table. And then of course, you ask yourself whether is it soluble in water. Okay, if it's soluble, okay, it will be maybe it's nitrate. Okay, or it can be some chlorides that are soluble, or some carbonates that are soluble, like all your group 1 salts. Okay, so page 2, some of the words that we'll take a look at will be precipitate and they are insoluble salts. Okay, So if you take a look, the one that you usually do in lab, you have aqueous solution. Okay. So once two aqueous solution are mixed, you see this. Okay. So this is what we call insoluble solid. Okay, they are called your PPT. And why is it solid? Because light cannot pass through. So the yellow solid form here, light cannot pass through, so it's a solid. Okay, so only when you cannot see through, then you call it precipitate. Otherwise, it will be a solution. Okay. Then, of course, there are some common terms such as effervescence. Okay. And then you will also see sometimes you need to add excess. So there are two parts to it. Okay, we will take a look at it later on when we look at cations. Okay, so for gases, quite straightforward. There are a few gases to take a look at it. Okay, so ammonia, NH3, carbon dioxide, chlorine, hydrogen, oxygen, and sulfur dioxide. Those they are highlighted red. Okay, they are the new gases that we have not done it in lower sec before. So when do we need to identify or test for gas? Please take note, put a star here. When effervescence is observed and when you heat. So when effervescence is observed, you must ask yourself, what gas? Okay. Now during heating, you only use moist, red, or blue litmus paper. Okay, write this down. So only use moist, red, or blue litmus paper when you are heating. The rest you use spleen or you use lime water, etc. Okay. So all these are found in your SLS, the videos. You can go and watch how to test for them. So moving on to your notes, page 10. Okay, when we want to test for hydrogen, okay, we will use the lighted spleen. Lighted spleen has a fire, has a flame here. Okay. Now hydrogen is produced when there is a reaction between acid plus metal. Okay, so when you did your experiment, the metal that you used was magnesium ribbon, but you can use other metal. It can be zinc, it can be iron. It doesn't have to be magnesium, but it has to be between metal and acid. Okay, then you start to see effervescence. So this is your observation. You need to write down effervescence is observed. Okay. So when you react acid plus metal, you will see effervescence. Straight away you tell yourself, oh, effervescence, so I must test for gas. So when you see metal, how to see whether it's metal? When you see something is silvery, when you see something is shiny, and your metal must be a solid, then you can roughly deduce that, oh, this unknown must be a metal, and then when I react with acid, I will produce hydrogen. So you must prepare lighted spleen beforehand. Why prepare beforehand? Because your gas will escape, right? So you don't want it to escape. So you must quickly prepare your Bunsen burner. Okay, open the air hole once it's lighted. Then you start to test for gas. Okay, so this one will be quite easy. Lighted spleen will extinguish with a pop sound. Okay, so why do you hear the pop sound? Because it's flammable. So if you have a lot of hydrogen, then the pop sound will be bigger. Okay. Next, of course, oxygen. Insert a glowing splint. Okay, it will just be an amber here. So there will be no flame. Okay, likewise, please write down. Your first observation will always be effervescence is observed. That's your first one. Then you observe effervescence ready, right? Then you take out your glowing spleen to test. So your glowing spleen will rekindle. Reason being, you need oxygen to burn. Okay. Then moving on, carbon dioxide. So for carbon dioxide, you bubble the gas through the lime water. So this is a delivery tube. Please draw it. Insert all the way. Okay, insert all the way into the lime water. This is about 1 cm cube. You don't add too much. So this CO2, right, it will form a white precipitate. So your white precipitate will be your calcium carbonate. Okay, recall under your base, lime water is CaOH2. Then you add your CO2. Okay, this is your acidic oxide. This is your base. So acid plus base, you will form salt and water. So your water will be H2O. In this case, the H2O comes here already. So whatever that remains, okay, so whatever that remains, which is your calcium oxide plus the carbon dioxide, will be CaCO3, calcium carbonate. So calcium carbonate is insoluble. Okay, because what we learned for the solubility table is all carbonates are insoluble. So that's why you will see white PPT. Okay, for chlorine, chlorine is a greenish yellow gas and there's a pungent smell to it. Okay, so what we do is we use a moist blue litmus paper, and this moist blue litmus paper must be moist. It will turn red and then it will bleach. Why will it bleach? Because chlorine is actually used in bleaching solution. So that's why it will turn white. Okay, then next will be sulfur dioxide. So sulfur dioxide, okay, you look at this sulfur. This is non-metal. Then this is your oxygen. So non-metal plus oxygen, this is your non-metal oxide. So for non-metal oxide, I have more than one oxygen. Recall your base. This is an acidic oxide. Okay. So for this sulfur dioxide, it's colorless. It has a pungent smell, and we use acidified potassium manganate to test. Okay, we will need to add H2SO4, okay, and potassium manganate. So once I add, right, initial color, you must give me the initial color. Your color change must always be initial to final. So the initial color is purple. So purple will turn colorless. Okay, in this case, purple will turn colorless. This part here, don't need to worry. For now, not important. Okay, you can ignore. Okay, but at this point, you need to take note. Color change must always be taking note of the initial color to the final color, which is your colorless solution. Okay, or rather your filter paper from purple will turn colorless. Okay, last gas will be ammonia. So this ammonia, what we learn under bases, this is your weak alkaline. Okay, so whatever we learned so far, you need to use acids and bases. You cannot forget. Otherwise, this whole topic will be very difficult for you. Okay, so for weak alkaline, you use moist red litmus paper and it will turn blue. So why? Because this is an alkaline gas. So what did we learn so far? Okay, without referring to your notes, you test yourself. Okay, ammonia, what do I test for? Carbon dioxide, what is the test? Chlorine, what is the test? Hydrogen, what is the test? So on and so forth. Okay, so after we learn the different types of tests to test for gases, we'll move on to the next part, which is test for anions. Okay, so as mentioned, we have this unknown salt. Okay, and this unknown salt has unknown cation, unknown anion, and when reacted with acid, okay, it produces effervescence. Okay, so we can, at this point, okay, we can test for the unknown gas. What is the identity of the gas? Okay, so this one is done. Now we move on to the anions. Okay, there are a few common anions that we encounter. So these are the common ones: carbonate, nitrate, sulfate, chloride, and iodide. Okay, so likewise, we will construct knowledge about how to test for different anions. So I'll give you an example. Now I have two unknown here, okay, and they are solids. Alright, so I have copper 2 carbonate and copper 2 nitrate. But since the bottles are unlabeled, I need to do some tests. Okay, so the only thing that is different about between these two compounds will be the anions. One is a nitrate, one is a carbonate. Okay, so at this point, whatever that we learned so far, ask yourself, what reagent do you use to add into both bottles to distinguish these two? Okay, so pause the video, take some time to think before you move on. Right, so to identify between these two compounds, I will use hydrochloric acid. So I have two solids. Okay, I'm going to add hydrochloric acid into each. And then I realize for one bottle, I notice effervescence. Okay, I see effervescence for one bottle. Whereas for the other one, it's just colorless solution obtained. Okay, because you see, they are both aqueous state. Okay, so colorless solution is obtained for one and effervescence for the other one. So for the effervescence, I can conclude, oh, a gas is produced. Then this gas, according to what we learned earlier on, once we see effervescence, we need to test for gas. Okay, so from here, I can do a simple test and I realize, oh, the one with effervescence, right, when they react with acid, okay, is the carbonate. Okay, because carbonates, when reacted with acid, will produce carbon dioxide. Whereas for the nitrate, right, there's no gas produced. In fact, we never learned any reaction about acid and nitrate. Okay, so this is a simple way to test between carbonate and nitrate. Okay, so in your notes, page 7, okay, fill in the blank for this one for carbonate. Okay, so page 7, to identify carbonate, all we do is we add hydrochloric acid. Okay, so when we add hydrochloric acid, or rather when we add acid, okay, acid reacts with all carbonates to form carbon dioxide gas. So when you want to write down your observation, you do this step by step. First of all, effervescence is observed. Then this gives you a clue that you need to test for gas. Okay, so for carbonate and acid, these two or either one, okay, straight away you need to prepare your lime water. Okay, so please write down inside, prepare beforehand. Okay, you just need a test tube and you add 1 cm cube of the lime water and straight away you can test for it. Okay, so this colorless gas, which is a CO2, when they react with calcium hydroxide, which is a lime water, they will form a white precipitate called calcium carbonate. Okay, so this is your base, metal hydroxide. This is your acidic oxide. Okay, so these two will react to form your white precipitate. So when bubble together, you'll form white precipitate in lime water, and that tests for the presence of carbonate ion. Okay, so it tests for the presence of CO2, and this means that CO2 gas is produced between. Okay, now what happens if I have two bottles? Okay, now I have solutions. One is nitrate and one is chloride. So same thing, cations is the same. I need to test for anion. Okay, pause and think. Okay, for both bottles, I will add silver nitrate solution. Okay, for the one with copper 2 chloride, I will see white precipitate. Okay, so aqueous plus aqueous, I will see white precipitate. Whereas for the nitrate, and I add another nitrate, they are all nitrates. So this one is solution remains. Okay, so there's no precipitate at all. Alright, so in this case, I can tell that, oh, the one with white precipitate must contains the chloride. Because this chloride, when it comes together with Ag+, so I have my Ag plus cation, I have my NO3 minus anion. When I have this chloride, these two will attract, because minus will attract plus. Then when these two attract, then they become insoluble solid, which is what we call a precipitate. Okay, so to identify chloride, we use silver nitrate. Okay, so go back to this part. These are our common anions. One thing you need to know for this topic is your solubility. Okay, if you don't know your solubility, you cannot identify which one is aqueous, which one is solid, and whether a precipitate will be formed. So let's take a look. For the second anion, we will see nitrate. Okay, so unknown is nitrate. This is unknown. If my unknown is a nitrate anion, when I add sodium hydroxide solution and a piece of aluminium foil, okay, this process will release NH3 gas. So this is a gas. First observation, effervescence. Alright, second observation, I will use moist red litmus paper to test and it will turn blue. Okay, reason being, ammonia is an alkaline gas. Now this part here is for your information. So don't need to memorize. If you don't want to read, it's fine. Okay, it's just to show you that during this test, ammonia gas is released. Okay, why is it so? Don't need to know. But you need to know that test for nitrate is this test. Okay, you need to know observation and the test. Okay. Next one is sulfate ion. So similarly for sulfate ion, okay, I also don't know what is this unknown, and I add barium nitrate solution. So this is aqueous. Okay, so I have SO4 2 minus. Okay, I have Ba2 plus. I have NO3 minus from my barium nitrate. So my unknown contains sulfate. This unknown is an anion. Of course, it will be attracted to the cation. So you ask yourself, oh, when this sulfate and this barium come together, okay, will they form a compound that's soluble or insoluble? Okay, so this will form barium sulfate, and this is a white precipitate. So all sulfates are soluble except for bochap liao, meaning barium sulfate B, calcium sulfate, lead 2 sulfate. All these sulfates are insoluble. Okay, so this is a precipitation reaction. Okay, where I have my aqueous plus aqueous, and then I will have a precipitate form. So the reaction will be barium cation, sulfate anion, together they form an insoluble solid. Okay, then let's take a look at chloride. Page 8 of your notes now. Okay, so for chloride, same thing. So just now I have chloride ion, I add silver nitrate. This silver nitrate is Ag plus, NO3 minus. So when I have my Cl minus, these two will attract each other and they will form a white precipitate of silver chloride. Okay, so all chlorides are soluble except for silver chloride and lead 2 chloride. Okay, so sometimes the question will ask you, what is the identity of this white precipitate? You need to be able to tell me, oh, this identity is silver chloride. Okay, Then last ion will be iodide. Now iodide is similar to Cl minus. Okay, they are both in group 7. So group 7 means similar chemical reaction. So I also add silver nitrate. So silver nitrate, I have Ag plus, I have NO3 minus. Okay, so this iodide and this silver plus ions will be together. So they will form silver iodide. So this is a precipitate. However, the color is yellow. Okay, silver iodide is yellow. Silver chloride is white. Okay, so these are the few ions that we went through. Okay, without referring to your notes, I hope you ask yourself, okay, to test for these anions, what are the tests? You need to ask yourself this, then you will remember. Okay, so this is a summary. To test for carbonate, I use acid. Then I test for the gas evolve. If it's CO2, I can conclude that this unknown is carbonate. If it's unknown is nitrate, I add sodium hydroxide, I add aluminium. Must only be aluminium, cannot be something else, cannot be magnesium, cannot be zinc, must only be aluminium. Then I warm the mixture, I will see effervescence, and the effervescence I will test using moist red litmus paper. Okay, then for sulfate, I use barium nitrate. Chloride, iodide, I use silver nitrate. But before that, I always add nitric acid. So in the next video, I'm going to show you, alright, why do we add nitric acid? Okay, so this video is made by Mr. Jensen Tan, okay, to show you why do we add nitric acid. So after we finish anions, we are down to the last one, which is cations. Okay. Same salt, same unknown. I have already learned about testing for unknown gases, unknown anions. Okay, and then cations. Okay, So for cations, we are going to use two reagents. One is aqueous sodium hydroxide. One is aqueous ammonia. Both of them are alkali. One is strong alkali. The other one is weak alkali. Okay. So for cations, okay, one very simple way is to see the colors. All right. So for cations, there are transition methods. Okay. So certain cations, they will produce colored compounds. Okay, so you take a look at this slide here. Okay, these are the common ones, common metal ions. Okay, that will produce colored compound or rather colored solution. So I have titanium, vanadium, chromium, manganese, iron, so on and so forth. Take some time, pause the video, find where are these metals found. You will realize, okay, that these metals are found here. Okay, they are between group 2 and group 3. And they are groupless. Okay, so these metals, they form colored compounds and they are called transition metals. Okay, so they are metals, so they will form cations, just that their compounds are colored. Alright, so one important thing to note, okay, transition metal will form colored solutions, a colored compound. Okay, so take a look at this, A to H. I have altogether 8 solutions. So make a guess, okay, assuming their anions are the same, which of the following is likely or are likely to contain transition metal ions? What will your answer be? Okay, so A to E, they are colored. Okay, take some time to go and find out where are these metals found. Okay, magnesium is group 2, sodium is group 1, and calcium is in group 2. Okay, so A to E, they are transition metals. Whereas for F, G, and H, okay, they are group 1 and 2 metals. So you can see that their solutions are all colorless. For A to E, they're all colored. Okay. So first thing, once you see the unknown is colored, right, straight away, okay, tell yourself that highly likely it's going to be transition metal. In fact, in your syllabus, colored is definitely transition metal. So one thing you can recall will be copper 2 sulfate, the crystals is blue color because it contains copper 2 plus ions. Some of you have synthesized iron 3 sulfates, same thing, those are colored compounds. Okay, so if you see the picture on the right, those McDonald's Coca-Cola cups, they are colored because they contain transition metal. Okay, sodium chloride is from group 1. When it's solid state, aqueous state, they are both colorless. Copper 2 chloride and copper 2 chloride aqueous, one solid, one aqueous, they are also of different colors. So copper is my transition metal. So copper 2 sulfate, likewise, it can be blue, it can be white. So it can also form colored compounds when it's hydrated. Okay, now in the past, okay, we use colors to identify the different cations. So I have lithium, sodium, potassium, rubidium here. Okay, last time they used fire because different cations will produce different fire. Okay, so they realized that different cations produce different colors, so we just use colors to identify. Okay, so if you take a look here, all my cations all have different colors when they are burned. Okay, so they say, okay, just use fire. In fact, this idea of color is commercialized. So if you recall, National Day, they have fireworks. New Year countdown, they have fireworks. All these different colored fireworks contains different cations. Okay, so if I want something to be red, I ensure that my compound has lithium, or I want something to be green, then I have copper cations. However, they are not commonly used. They're not commonly used in testing for cations now. Any idea why? Reason being, they are not conclusive. They are not conclusive because lithium, okay, and strontium, they both look red to me. So it's not conclusive. Okay, so because it's not conclusive, we move on to using other reagents to test. Sodium hydroxide and ammonia. Okay. Okay, so let's take a look at your notes, page 3. Okay, for cation ions, we use two things to test for them. So instead of a flame test, we will use um, sodium hydroxide and ammonia solution. So why is it that we need either one, or why is it that we need to use aqueous sodium hydroxide? Then we still sometimes need to do another test, is because some tests, right, they'll produce the same result. So we need to do twice to confirm. Okay, so for example, my unknown contains group 1 salt. Okay, group 1. Okay, I will use sodium hydroxide first. And I know that this sodium hydroxide is aqueous, right? So I have Na plus. I will also have OH minus. Okay, so group 1 cations, when I add this inside, ignore the N ions, they're not important. So when I add this NaOH inside, these cations will attract the OH. So these cations, when they attract the OH, okay, so when they attract the OH, they will form NaOH, or they will form KOH. And we know that even if these are formed, right, group 1 salts are all soluble. So I have my unknown, okay, my unknown with Na plus, and then when I add NaOH inside, I add a few drops, I add excess, no matter what, in the end, I will still get a solution. It will still be aqueous, no precipitate, because they're all soluble. Okay, so this is how I test for cations. Alright, now moving on, let's take a look at ammonium salt. Likewise, for ammonium salt, I will add a few drops of NaOH first. Add a few drops first, then I shake, then I add excess, then I shake. Okay, so for this case, I have my NH4 ion, cation, and then I add my sodium hydroxide, which is Na plus and OH minus. So this cation will definitely attract my OH, right? So we all learn in solubility table that ammonium salts, all ammonium salts are soluble. Okay, so all these ammonium salts are soluble, and when they react with my NaOH, okay, if you recall your reaction, okay, your ammonium salt plus alkali. So you recall your alkali reaction because NaOH is an alkali. What do you all recall? Ammonium salt plus alkali, you will form salt plus water plus ammonia gas. Okay. So this ammonia gas is my effervescence. Okay. So I have my ammonia gas, okay, which is my effervescence. I will test for this gas using moist red litmus paper, and it will turn blue. Okay. So this test tells me that, oh, if I use NaOH, it's no precipitate one. I add a few drops, no precipitate. However, for part B, I add in excess. Then I start to heat. Then I realize, oh, I start to heat. Oh, it will produce effervescence. And to test for the effervescence, because heating, right? Heating can only use litmus paper. So I use litmus paper to test, and I realize, oh, red color become blue. So I conclude that this unknown is ammonium cation. Okay? Okay, moving on. What if my unknown cation is zinc? Okay, what if my unknown cation is zinc? So same thing, I will use NaOH. Okay, I add a few drops first. Okay, so my NaOH, I have my Na plus, I have my OH minus. Okay, so this NaOH, okay, so this Na plus and OH minus are added into this solution with zinc. So I have Zn2 plus. Okay, so I have my NaOH inside. So of course the zinc cation will attract my hydroxide, right? So I will form ZnOH2. Okay, then we recall solubility table. All hydroxides are insoluble except for group 1. Okay, so in this case, zinc is not in group 1. Okay, so this is insoluble. Okay, however, when I add excess, okay, this white precipitate will dissolve to form a colorless solution. Okay, so in this reaction, my white precipitate will react. Okay, what is the reason being here? This one is same thing for your information. Okay, it's for your information. So fill in the blank for this part here in your notes. Okay, you have a zinc cation. Okay, then you have 2OH minus from your sodium hydroxide. They will form an insoluble solid called zinc hydroxide, and this is your white precipitate. Okay. Okay. For aluminium, same thing. All right. I will add my NaOH inside. Okay. I will have Na plus, OH minus, and then I will also have my aluminium cation. So the cation will attract the OH to form aluminium hydroxide. So same thing, all hydroxides are insoluble except for group 1. Okay, so when I add a few drops inside, this will form white precipitate. Okay, so the equation will be like this. Aluminium 3 plus equals plus 3 hydroxide, and this will form my white precipitate called aluminium hydroxide. Okay. Now, if I were to add excess of my NaOH, all right, this white PPT will react. Okay, and then they will just react away to form a colorless solution because they will be aqueous. So same thing, this one also for your information. Okay, all right. Okay, and the explanation is the same for your lead cations. Okay, when I have my lead cations inside and I add a few drops of NaOH, okay, okay, it will react with the anions from the sodium hydroxide, and it will form lead 2 hydroxide, which is a solid. Okay, and likewise the precipitate form when I add excess, okay, it will form a colorless solution. Okay, so for zinc, aluminium, and lead, when I add excess NaOH, okay, the white precipitate form dissolves. I repeat, for zinc, aluminium, and lead cation, when I add excess, the white precipitate form will dissolve. Okay, so you take a look, these three, what do you notice? Sounds familiar, Zeb? Okay, they are your amphoteric oxides, right? Which means they are also amphoteric hydroxides. This one is just for your information. Okay. However, you need to memorize this, that for ZAP, zinc aluminium lead, their white precipitate dissolves in excess NaOH. Their white precipitate dissolves in excess NaOH. Okay, so you will need to know these three. So how to remember easily? Just remember ZAP. Next is your calcium. Now calcium likewise, okay, it will form white precipitate because you have your Ca2 plus equals plus OH minus equals, and then you have Ca OH2. So you have white precipitate. However, when you want to add in excess calcium, they are not ZAP. So they cannot dissolve in excess NaOH. So this white precipitate will remain insoluble. Okay, they will remain insoluble. Alright. Okay, so moving on to transition metals. Transition metals quite straightforward. Okay, for copper 2 plus ions, okay, it's the same. You have Cu2 plus equals plus OH minus equals, you will form copper 2 hydroxide solid. All hydroxides are insoluble. So you have blue precipitate form. When I add in excess, they are also insoluble because they are not zinc, they are not aluminium, they are not lead. Okay, this is blue solution. Iron 2 is pale green solution. Okay, same thing. Iron 2 plus equals, when you add with sodium hydroxide equals, you will form insoluble iron 2 hydroxide, and that is your green precipitate. Okay, but this green precipitate will turn brown when it's exposed to air. This is what we call your rust. You know, the rust on iron nail or metals, they are reddish brown, so they are iron 3. But so this iron 2 hydroxide, iron 2, when I add sodium hydroxide, I will get this green precipitate. Same thing, this green precipitate will remain insoluble. For iron 3, okay, the solution usually is dark yellow or orange. Okay, so for iron 3, it's the same thing. Okay, for iron 3, you have your iron 3 plus cation plus hydroxide and ions from the sodium hydroxide. You will get iron 3 hydroxide, and that is reddish brown color. Okay, so that is the reddish brown color. Likewise, the precipitate is insoluble in excess NaOH. Okay, let's turn to page 12 of your notes. Okay, page 12 of the notes. Some of you might be wondering, how come we learn aqueous sodium hydroxide, we still need to learn aqueous ammonia? Okay, reason being, you see, I have my insoluble, or rather, reason being, I have my unknown cations. And then these unknown cations, okay, they are colorless solution. Okay, so I need to distinguish them. So I distinguish them by using sodium hydroxide. So I add a few drops. When I add a few drops, they have white precipitate. Then when I add in excess, all these white precipitate will dissolve and become soluble to form colorless solution. Okay, so I have my 3 clues here. So question is, how? How do I narrow down? For example, how can I confirm that it's zinc? How can I confirm that it's lead? How can I confirm it's aluminium ion? I can't because I have three choices here. Okay, so that is why there is another test which we use aqueous ammonia. And this aqueous ammonia likewise also produce OH minus. Just that this is a weak alkali. Okay, low OH minus. But it will still produce OH minus. Okay, so I will not go through everything in detail because they are similar. Okay, however, you realize just now my sodium hydroxide, I have three together. They all have the same reaction, same results. However, if I use aqueous ammonia, if my unknown is zinc, I will have my white precipitate that is soluble in aqueous ammonia. But for lead and aluminium, this white precipitate form, they are insoluble. So that is why I do a second test using aqueous ammonia to further distinguish them. Okay, so the white precipitate here is the same. This white precipitate, you can write down, is still zinc 2 plus. Okay, and then I add OH minus, and I will get zinc hydroxide solid. So it's still the same. Then this precipitate is also the same. I will have aluminium 3 plus my hydroxide. I will still form this white precipitate called aluminium hydroxide. It's still the same. Okay, it's still the same. Just that this remain insoluble now because this one is a weak alkaline. Why is the reason like that? It's not really that important. Okay, if you want to know, please read it up yourself. Okay, so this is the summary of test for cations. Why we use sodium hydroxide and why we use aqueous ammonia, because we want to confirm the test. Okay, so for example, for copper, sometimes they will have different reactions. Okay, so you see for copper, my blue precipitate is insoluble. But if I use aqueous ammonia, it will be soluble to form a dark blue solution. Okay, so all these are the results of observations. So all these are the observations. Please see how we record the observation. We always have white precipitate. Okay, this is a few drops. And then this is step number 1. Then we add in excess. Okay, so we always have step 1 and step 2. Okay, so watch the video in SLS already. Okay, these are the results that you get. Okay, which is already given out to you, and you see that, oh, okay, I have all these white precipitate form. When I add excess, the second column here, okay, when I add excess, I have different results. Okay, for zinc, aluminium, lead, okay, whatever that is formed for my white PPT, they are all soluble. And this is only for ZAP. Okay, but for aqueous ammonia is different reaction, so don't confuse them together. Okay, then for my copper is blue, iron 2 plus is pale green, then iron 3 plus is pale orange. Okay, I have a question here. All right, now put a star. I want you to think about how do we distinguish lead 2 plus and aluminium 3 plus. Since you notice, I add both, the results are the same. So I cannot distinguish them. So what is the third test? Okay, it's something that we have learned in test for anions. What will that be? So the answer is I add aqueous equals what? Sodium chloride or anything. So I can add any aqueous chloride solution. Okay, so I have my Pb2 plus. I have my Cl minus. These two will form white PPT. Okay, so whatever we learn in anions, we can also apply here. Okay, so that is all for test for cations. We use two different solutions: sodium hydroxide, aqueous ammonia. Okay, now the case is here. So I drank this unknown. All right, and now you're equipped and you have all these tests done. Okay, and these are the observations. So your job is to identify the salt and share with me your answer